All right, let's dive into something that sounds like it's straight out of science fiction. We're going to talk about a completely new kind of computer, one that isn't built but grown. A machine that is, for all intents and purposes, alive.
I mean, really think about that for a second. What if your computer wasn't made of silicon and metal, but of living brain cells and fungi and weird liquid electronics? And what if it powered itself with the kind of chemistry that might have sparked life on Earth billions of years ago? Well, that's not just a thought experiment anymore. That's what we're exploring today.
Okay, it has a bit of a mouthful of a name. SQFMB. That stands for Symbiotic, Quantum-Fluidic, Mycoid Biocomputer. But the most important word there, the key to the whole thing, is symbiotic. This isn't about just jamming a computer chip into living tissue. This is a vision for a totally integrated ecosystem where biology and electronics grow together, work together, and become a single living thinking machine. So how are we going to wrap our heads around this? Here's the plan. First, we'll look at the living wetware, the brains and nerves of the operation. Then we'll get into the wild stuff, the liquid wiring and a little dose of quantum theory. After that, we'll see how the whole thing powers itself. And finally, we'll ask the big question. What does this biohybrid future actually look like for us? Okay, first things first, we have to understand the two biological powerhouses of this system. You've got the processors, the things that do the thinking, and then you've got the living network that connects everything together. At the very core of this living machine, you'll find something called brain organoids. Now, what are those? They're basically tiny 3D clusters of human brain cells grown from stem cells. You can think of them as mini brains that naturally organize themselves into complex neural circuits ready to process information. So how do you teach a mini brain? Well, it turns out it learns a lot like we do, through positive reinforcement. It gets some kind of input, it processes it, and if it gets the right answer, it gets a little reward, a sort of feel-good chemical pulse. And this isn't just a theory. This exact method was actually used to teach a layer of brain cells on a microchip how to play the old-school video game Pong. Seriously. And this is where you really start to see why this is such a game changer. Just look at the comparison to a traditional silicon-based AI. The organoids use a tiny fraction of the energy. They can learn from just a handful of examples and are constantly adapting, while current AI needs gigantic data sets and has to be retrained all the time. It's just a more natural, efficient, and, well, organic way to compute. Okay, so you've got these incredible mini brains, but how do you connect them all together? You don't use copper wires, you use a fungus. Yep, the root-like network of a fungus, called a mycelium, provides the living scaffold for the whole system. It's literally a biological wood wide web for this biocomputer. But the fungus isn't just sitting there like a passive bunch of wires. No way! It's an active part of the team, doing 4 critical jobs. It provides the physical structure, it acts like blood vessels to transport nutrients, it carries electrical signals, and, get this, it even does its own form of computing by remembering the signals that pass through it. So we've got the brains and the nerves, but how on earth do you plug these soft, wet, living things into hard electronics? The answer is just as weird and wonderful as the rest of it. You use liquid wires and a little bit of quantum mechanics. This is all possible thanks to a field called iontronics. Now, your typical circuit uses electrons to carry a charge. Iontronics uses ions, the very same charged particles that our own neurons use to send signals. This means the circuits can be soft, totally biocompatible, and run on incredibly low power. They can form liquid synapses that speak the same chemical language as the cells. And these liquid wires are more than just connectors. They can be woven right into that fungal network, creating this amazing, flexible mesh of circuits that can actually reconfigure themselves on the fly. And just like the fungus, they have memory. They can store both short-term and long-term information, adding a whole other layer of computing power to the system. And now, this is where things get really wild. The design includes a theoretical piece called Posner molecules. The thinking is that these little clusters of calcium and phosphate could act like tiny shields protecting quantum-entangled particles from the noisy biological environment. This could, potentially, allow the system to tap into the power of quantum computing, embedding quantum memory right into the living tissue. Okay, before we get carried away with quantum brains, we need to pump the brakes for a second. It is absolutely crucial to point out, as the researchers themselves do, that this quantum part is highly speculative. It's an incredible idea for the future, but right now, there's no direct evidence for it in living neurons. So, think of it as an exciting possibility, not a proven fact.
All right, every computer needs power, right? You plug it in. Well, this computer doesn't have a plug. It has its own internal engine, a self-sustaining geochemical power plant. The power source is something they call a chemical garden, and it's designed to mimic the deep-sea hydrothermal vents where many scientists believe life on Earth first got its start. It's a tiny, self-contained reactor running on the kind of simple chemistry you'd find on a young planet. The process itself is surprisingly straightforward. You have these iron and sulfide solutions mixing together in a heated chamber. That reaction constantly produces hydrogen gas, and that hydrogen is then captured by tiny fuel cells that turn it straight into electricity. The result? A slow, steady, sustainable trickle of energy to power the whole living system. So let's just step back for a second and put all the pieces together. You have the brain organoids as the processors, the fungus as the structure and communication lines, the iontronic circuits as the biocompatible wiring, and the georeactor as the power supply. What you have is a fully integrated, self-powered cyborg ecology, a system where the line between machine and organism just completely melts away. And that brings us to the billion-dollar question. What would we actually do with a living computer? Because a technology this revolutionary opens up a universe of amazing possibilities, but it also comes with some serious risks that we absolutely have to approach with caution. The potential applications are pretty incredible. Imagine ultra-low-power living sensors monitoring the health of a forest or an ocean, or biological coprocessors that could make our current AI systems drastically more energy efficient. We could even use them as tiny labs to study how life itself began, or create mind-bending bioart that makes us all think about our future. And this is where the stakes get incredibly high, because for every amazing best-case scenario, like green AI or new medical breakthroughs, there's a terrifying worst case: weaponization, runaway organisms, accidentally creating something with consciousness. The path we end up on depends entirely on the choices we make right now. To make sure we steer towards that better future, the researchers proposing this are also demanding a strict set of safeguards they call non-negotiable. Things like built-in biological kill switches, constant monitoring for any hint of consciousness, and having ethics committees involved from day one. They're treating this not just as an engineering challenge, but as a massive ethical responsibility. You know, in the end, this whole idea isn't just about building a faster or more efficient computer. It's about a totally new way of thinking about technology. I love this quote. It describes it as a living bridge between Silicon Valley and Earth's crust, a kind of technology that works with nature instead of just consuming it. And so that leaves us with one final huge question to think about. As we keep blurring this line between machine and organism, between silicon and the living cell, what exactly is it that we're creating? Is it just a powerful new tool? Or is it an entirely new form of life?